Let's now look at one of the most important principles of deep learning in practice, transfer learning. Training modern, large-scale confidence on ImageNet, or even larger datasets, can easily take several weeks on dozens of GPUs. So you may be a bit intimidated and ask yourself whether you will ever acquire the skills or have the resources to do that. The good news is, for many practical applications, you won't have to. Instead, we can stand on the shoulders of giants and build upon large-scale confidence pre-trained by other people. And this is what transfer learning is about. Suppose you want to build an app for recognizing flowers, and you've gathered 1,000 images of 100 different flowers. So you now have 10 images per class. Now the problem is, training a large-scale ConvNet from scratch won't work in this case, since you simply don't have enough data. And this is where transfer learning comes in. You train a large-scale ConvNets on a huge dataset like ImageNet, or you just download the weights trained by someone else. And the idea is, because it has been trained on a huge dataset to perform a complex classification task, the convolution layers have learned to extract powerful image features that we can reuse for a slightly different task. So now we throw away the 1,000-way classification layer and we replace it by a 100-way softmax layer for your 100 classes of flowers. But we keep the weights in the convolution layers. Then we fine-tune the network to the task of flower classification. And because the convolution layers are initialized with the weights trained on ImageNet, we expect it to perform substantially better than training from scratch, where we're heavily limited by data and would easily overfit. For transfer learning, there are basically two different approaches. The first, we train only the classification layer and completely freeze the weights of the backbone. This approach is fast and simple, since we don't have to backpropagate gradients through the convolution layers, which saves us memory and compute. The downside is that the features learned from ImageNet may not be ideal for the target tasks, such as flower classification, so fine-tuning the feature extractor often helps. This approach often leads to better performance, but is more costly and requires some care in choosing the learning rate and making sure to avoid overfitting, for instance by performing early stopping. Now, transfer learning is not only applicable to classification, but is a much more general concept. For instance, if we want to perform object detection, we can follow the same approach. Object detection is a little more complicated than classification, so instead of the single classification layer, we add a few extra layers or subnetworks. But again, we don't start from the image, but we build up the convolution layers trained on ImageNet, and then we use them as a feature extractor. For instance, the first deep learning architectures for image segmentation were done this way. They added a pixel-wise classification on top of pre-trained AlexNet. Object detectors often work by generating proposals for bounding boxes on a regular grid. They then perform operations like refining the box coordinates or classifying them into background or object for each box. Here, transfer learning is also a common approach. To use a convolutional net pre-trained on ImageNet, and then add small networks consisting of a couple of layers to perform the box-specific tasks. These were just two examples of image recognition tasks where transfer learning is used. The list is much longer and includes things like pose estimation, image captioning, or scene graph prediction, and of course many, many more. For the exercise, we're going to use a ResNet pre-trained on ImageNet to perform transfer learning for classifying Pokemon. Before you start though, think a moment about which approach you expect to work best. Training ResNet from scratch, training only the classification layer, or fine-tuning the entire network.